Okay, cool. Hi, everybody. Thank you for joining us on this rainy afternoon to talk about FloodNet NYC. My name is Polly Peroni. I'm the project manager for FloodNet. I'm based out of the Science and Resilience Institute at Jamaica Bay, which is based out of Brooklyn College. And I'm accompanied today by teammates from NYU Center for Urban Science and Progress, as well as Pratt's Spatial Analysis and Visualization Initiative. I'm going to give a brief overview of FloodNet NYC, and then we'll talk about three different data products that are part of our project that are in different stages of development. As you can see on this slide, FloodNet is a collaboration between several different partners. In addition to the ones that I named, we also include the Advanced Science Research Center, another CUNY campus, and several New York City agencies and community organizations as well. We collect real-time, hyper-local measurements of street-level flooding across New York City using sensors like the one illustrated. Well, it's on the stop sign. It's kind of hard to see, but Charlie also can hold up an actual FloodNet sensor, just like the one in the photo. The flooding that you see in this photo took place in Hamilton Beach, Queens on September 29th of last year, and we'll talk a little bit more about that flood event as we move forward. So our mission at FloodNet is to develop tools for real-time urban flood monitoring, implement these tools across the city, and then make that data and those tools as accessible and useful to our stakeholders as possible. And our project motivation, our project was born out of a few different kind of community needs combined with interest from the city, but we've identified use cases for each of these different stakeholder groups, which are listed here. As flooding in NYC continues to increase in frequency and severity, we hope to enrich existing qualitative data sets with real-time quantitative measurements all across New York City. So just to provide a little bit more context about how FloodNet came to be, I wanted to spend a brief moment talking about the Community Flood Watch project. This is a community science research project, again, at the Science and Resilience Institute of Jamaica Bay, where I'm based, also funded by New York Sea Grant. FloodWatch is a project that helps New York City communities leverage photos to document what causes flooding in NYC neighborhoods. They've been doing this since 2018. You'll hear a bit more about this project later from John, but I just wanted to highlight them here because part of how FloodNet came to be was because Community Flood Watch was collecting flood photos and giving folks a way to share those photos and better understand where flooding is taking place and when. And some of the community members who are part of that project wanted some quantitative data that could provide additional context. So this was one of the first, these communities around Jamaica Bay were one of the first places where we started to install FloodNet sensors. So here's a bit more information about our sensors. We wanted a sensor that could sense water depth with an accuracy within 25 millimeters, collect and transmit measurements once a minute, be independent of existing power and networking infrastructure, meaning that you don't have to plug it into an outlet anywhere, and be as low cost and as rugged as possible. And we were able to achieve that, which is great. So our sensors are solar powered. They're mounted to drive rails around the city with permission from the Department of Transportation. And originally we started off using LoRaWAN as our network, and we've transitioned recently to cellular data transmission, which has eliminated some logistical challenges. And here's a photo of what those sensors look like in the field. So again, our sensors are ultrasonic, meaning that they send an ultrasonic pulse straight down toward the sidewalk. That pulse comes back to the sensor, gives us a distance measurement, which we then convert into a depth measurement. Most of the time, they're just looking at the sidewalk, telling us it's there. But when floodwater starts to rise, we'll see a gradual decrease in that distance, which tells us that there's flooding on that street or that sidewalk. The nature of our sensors also means that they occasionally measure other objects. They tell us that there are garbage bags, for example, underneath the sensor, or like a person has passed beneath it. We have developed robust kind of filtering pipelines to eliminate as many of those anomalous measurements as possible. I think Charlie and Bea might get into that a bit more later, and we're still improving those tools. But yeah, that's a bit of information about the sensor. The first data product that we're going to discuss is our data dashboard. Like you saw in our mission statement, it's always been a key goal of FloodNet for our data to be publicly accessible. And this is one of the first tools that we started developing for that purpose. Yeah, we started working on this data dashboard back in 2021 in the early stages of the FloodNet project. We hired a company called FieldKit to build a site based on kind of a series of workshops with New York City residents, researchers, and city agencies that we expected to all be interacting with the data dashboard in some way. So this is the main page. If you visit that URL, which you're welcome to do, you'll see a map with a bunch of circles on it. Each of those represents a FloodNet sensor. We currently have 87 sensors in the field. And then the number inside that circle tells you what that sensor is measured, like the depth that sensor is measuring in real time. So if you go on the dashboard right now, I think you'll see a bit of flooding in Staten Island and also City Island because of the heavy rainfall that's happening as we speak. And the gray circles are just sensors that are currently down or that were down when the screenshot was taken. I think there are less sensors that are down right now. I think that's the dashboards. To give an example of what this dashboard would look like during a severe stormwater flooding event, this is a screenshot that I took on September 29th of last year when we saw really heavy stormwater flooding all across the city. 26 of our sensors measured flooding during the storm. I think we had around 83 at the time. And there's a photo here of the intersection of Carroll Street and 4th Avenue in Gowanus. A lot of you probably saw this image on social media. There's a vortex where the flooding is starting to drain. So we actually measured a maximum flood depth of 36 inches at that location during that flood event. But again, we measured flooding in several other neighborhoods as well. And so actually, if you look at in South Williamsburg, there's a 24-inch reading, and I can show what the ultimate kind of shape of that flooding curve looked like. So this is, if you click on one of those sensor icons on the data dashboard, you will then be directed to one of these data view pages, and you'll see the most recent data from that sensor, and you can navigate the page using the scrubber bar below or by clicking around on the graph. So this is September 29th, and it shows about 3 hours of flooding. You can see that the peak depth was around 25 inches, and the histogram here is precipitation at a nearby weather station hosted by New York City Micronet. So that's another feature of our dashboard. You can add precipitation data sources as well as tide data sources where relevant to kind of think about what informed the flooding. It's also a way to interpret if you're not sure if something is a flood. So that was from the 29th. Something else you can do on the dashboard is compare data from different sensors that measured flooding during a single event. So this is that Carroll Street and 4th Avenue sensor. You can see that the onset of that flood was a lot more rapid than it was in South Williamsburg, but drainage was also a bit faster. Again, that could have to do with a variety of things. Precipitation varies across the city, but it can also help us to think about what's happening in the drainage systems during a major flood event like this. Yeah. There are also a lot of different ways you can interact with this page. You can select a certain time range of data. You can input into a calendar. And this dashboard is continuing to undergo development, especially the mobile view. So if any of you are looking at it on your phone, there are certainly things we would like to improve about the mobile experience, and we're working with FieldKit to kind of build out that scope a bit more. Sweet. And then while we've been able to measure a few very significant stormwater flood events that affected the whole city, the majority of floods we have measured have actually been in communities around Jamaica Bay, as well as on City Island, that experience more frequent flooding due to high tides throughout the year. That's often referred to as sunny day flooding because there doesn't have to be rainfall for flooding to happen in these communities. So the visual on top is actually from a paper that we have been working on, and it shows a pattern of flooding from December 2021 to May 2023 at one of our sensors on the Rockaway Peninsula. We actually measured over 120 separate floods at this location during that time period. The sensor has continued to measure floods since then. This is just the graphic that we happened to make. And then you can look below. This is another screenshot from our data dashboard. So this is about a week, week and a half of flooding in June 2022. Again, we can overlay that tidal data and start to think about the thresholds at each sensor for when you're going to start to see water come up and be measured. And that tidal data comes from a USGS tide gauge in Jamaica Bay. And then here's another example of tidal flooding. This is, again, comparing different FloodNet sensors in Hamilton Beach. These measurements are just from the beginning of March when a high tide coincided with very heavy wind and created deeper tidal flooding than usual. So we saw 2 feet of water at our Hamilton Beach sensor on Davenport Court. Yeah, and here's that dashboard again. So again, feel free to visit the link if you'd like. I can take any questions specific to this part before I pass it off to John to talk about our neighborhood flood reports. Yes.
So I've looked at USGS stream flow data before, and that has a little bit of a lag on its real time. Does this have some sort of a lag? And if so, how much?
That's a good question.
I'd say it's probably around, because there's a pipeline that we have in place. So when a sensor transmits, it hits our server. That's pretty much real time. Like it's a few seconds delay. We sense every minute. We do buffer some number of samples because we feed them through into a machine learning model, which is trying to detect anomalous measurements, so non-flood events. I don't know, you were like a few minutes?
I mean, we're like very conservative about like how long we're holding points, so we're really only a minute behind at most.
So not nearly as long as you guys.
Yeah, which is why we see a bit more noise, just because it's harder to do it at that time scale. So.
Yes?
How do you guys store the data? Do you store the data in the relational database or time series database?
It's a Postgres database with a plugin called Timescale DB running on it. So it's a time series database, but still relational. So we have a combination of regular relational tables and then hypertables, which are the kind of Timescale DBs, time series optimized tables. So all of the depth data is in a time series table. So we've got all the benefits of like high-speed access and aggregations and all the great tools that Timescale brings, plus the ease of use of a relational database. Because we were using Influx before, and it was great, but it was just difficult, and it was hard to bring people onto the team and then train them on the use of Influx, because it has its own language, its own querying language, which is more people know SQL than they know Influx, Flux, like Flux language. Yeah, but so far so good with Postgres and Timescale.
Yes.
How do you choose where the sensors go?
That's a great question, and is a question that comes up a lot both in community and in our interactions with the city. Part of what has shaped the sensor network that you see on the screen now has to do with technical and logistical considerations associated with the beginning of the project. At the very beginning, we were trying to install sensors fairly close to where our campuses are in order to be able to monitor them more easily. Sensors are also a bit clustered on this map, and that has to do with, again, that we were using a different network before for transmitting data. So we had to install our own gateways so that sensors could transmit, and that forced us to cluster. Luckily, with cellular, we're able to spread out a bit more. So we're in the process of actually accelerating our sensor installations quite a bit. And in order to do that, we've brought in a lot of data from the city and from our community partners, basically in the form of sensor suggestions to gain insight about where all of these folks have observed flooding to be happening. We're combining that with a systematic analysis, kind of a census tract scale analysis of flood hazard, flood exposure, and flood vulnerability. So hazard is coming from a couple of different flood maps, a stormwater map and a tidal flooding map. Exposure has to do with population density. And then we've been collaborating with a team that the Mayor's Office of Climate and Environmental Justice has put together to study flood vulnerability and using their index as well. So it's taking all of those suggestions and combining them with that analysis to generate locations. It's a process, for sure. Yeah. Sure. Yeah.
Do you guys have a goal, like how many sensors you plan to put it out each year for the following years?
Right. So our funder is the Department of Environmental Protection. We have a contract with them to install 500 sensors, and that's what's been accelerated. So we're hoping to install those sort of within a year, get to those numbers, a year or so, give or take. But as we move forward with this project, we're learning a lot about how many of these devices are actually necessary, and likely there will be locations that we haven't been able to get to, and we hope to continue to expand the network into the future. Yeah. I'm going to pass it off now, and then we can save any other questions.
I'm going to talk about another data-related product called Flood Local Reports, we've been referring to it as. And I am representing SAVI, the Spatial Analysis and Visualization Initiative of the Pratt Institute. The projects have been going on for a while, so since it started, I left my job, I started different things, but this has been going on. But if you don't know SAVI's work, we used to, and they still do work with a lot of NGOs, providing them with data analytics and mapping capacity. Please take a look. All right. So When we first started the project at Katie Graziano and Brett Branco, they had an kind of a not very fully formed idea about a reporting mechanism that could transfer all of the information from FloodNet, from FloodWatch, from 311 to the residents with a lot less friction, let's say. And because we have two very distinct data sets here, FloodNet is creating a machine-produced data set. It is extremely high resolution. There's lots of zeros in it. There are sometimes like some misreadings and things that every sensor has it. And on the other hand, we have a qualitative data set, which is FloodNet, FloodWatch. It is just people reporting floods themselves. So if they see a flood, they can go out their door or open their windows, take a picture, submit it. And so it has a much different resolution, but also have a much different meaning as well. If you tell someone, well, there's 4 inches of flood in front of my house, it's kind of hard to imagine what it means. Yeah, it's like this much. But if you have to take your child to the school through 4 inches, it means a lot different. Or if you cannot move your car out of your driveway and you skip a day of work because of that, it's a very different experience, right? And so we were thinking, how are we going to manage these two things? On top of it, there was a demand to include 311 data as well, and it also comes with its own issues, such as some of the community members that we spoke to, they said they never report flood because no one has ever done anything in their lifetime. They were kind of bitter about it. But some neighborhoods are much more positive about their experience with it, right? So what we've done is at the very beginning of our study, start Googling what are the flood-related tools that are around for the residents to look at. I believe our initial list was 13 of them. We deleted some of them because not all of them were extremely immediately New York focused, let's say. And we asked in community meetings to people, have you ever heard of this tool? Have you ever used of any of this? And out of our 13 tools, only the Stevens Flood Advisory Map that everyone knows about. Everyone used it, and although it's very complicated, the visualizations are not immediately understandable. I think people have developed a kind of a relation to it. But this about 2-3 years ago, I think that your dashboard was not really fully up and running at the time, maybe. So, it kind of told us a lot. Why do we have 13 tools if no one is really using them? We asked them, why are you not using? They're like, I didn't know I was there. Why would I? So there was some kind of a miscommunication because new tools were being published at the time as well, right? Like the stormwater flood maps and whatever, they're recent, relatively recent at least. And we started with a community meeting. This one was attended by community representatives, I would say, kind of people that you run into quite a lot in the flood-related meetings, like the Coney Island Beautification Project was there, East Hamilton something was there. Like all of those people that you usually know. And of course, you have a very educated crowd who sometimes know how to interpret the data better than you. They've been looking at it all their lives. But we have run like several hours long community meetings and got a lot of notes from them. There were like interesting things to learn. One of them is you can report things in 311, but you're faced with something as big as climate change, or like the city has to do such big things to address your comments. It is kind of impossible to answer to it, right? If it's closed, it doesn't mean it's mitigated. It's very hard. The way they shared information was very different than we thought. They were all in these closed Facebook groups. I think at the time, Katie would just post things in them. And I really like this one. Does anyone go to community board meetings? I think it was kind of like the bitter side of the attendees that were just frustrated. Yes, it's flooding, can't you see? Kind of attitude. But we usually don't like to go to meetings without anything to show. It's easier to talk on something rather than about theoretical things. So right before the meeting, we designed the layout. It was very primitive at the time, but at least had the data in. And we had a little map about where the 311 request came from, flood watch reports came from, how much flooding it's observed on a map and things. And of course, the residents were not necessarily happy about every single aspect of it, that their houses can be identified with flooding nearby. They thought it could reduce the value of their housing. Of course, like a lot of people's investments are tied to their housing, right? So you can't really blame them. But we tried to include some of the 311 data, some Pluto data. FloodNet data was simpler at the time, and we didn't know how to deal with a data set with so many zeros in it, because floods, thankfully, it doesn't happen every single day. And then 311 is at upright. It's filtered only to flood-related events, and we try to put as much photos as possible. And this is, I had the date, yes, 2021. All of these were like stored in separate places, and it was kind of difficult to get it through. The flood watch data was not living in a single place. I think they had a Airtable that was running. I recently made all of them available in the MyCoast. It's another database. Yeah, we just talking, we identified a few things that our report needs to address. So one, it needs to be very easy to access. The report itself as well, and also the information in the report, obviously. And so they're very easy to access, literally meant for people printed. So they could take it from someone and give it to someone else. They said, I want to throw this on my community representative's desk and leave or something. It needs to be up to date or updatable somehow. So the recent information is included. They can show, didn't you see the flood that happened last week? I think at the time in the first meeting, we had participation from a crowd that had a very advocacy-minded crowd. So that changed later on. We were a little bit misguided by that. They wanted to have all of the interactions that you can do with interactive dashboards and whatever. They didn't care at all. Yeah, and Facebook. Everything always ended up coming back to Facebook. Can we share it on Facebook? What can we do? It was like very important. I don't know if after many years, is it still Facebook? But it seems like the closed community groups are kind of the thing still. And also, I think 2021 is when a lot of crackdown for data sharing and social media platforms were starting. So we looked into it. It was possible at the time, and slowly everything closed. Even Twitter closed afterwards. Like, it's not that easy to share things. So after this meeting, we took comments, we did designs. We got an additional grant together with the Sea Grant and Cornell. I think I'm saying it right. And then we organized 7 more community meetings. The general topics that were discussed is that how do people access this with this new group? Is it still printed? Is it through internet? Is it through mobile, desktop? We talked a lot about if they can read every single visualization. Now, after 7 meetings, I can say it was a terrible idea. There was long discussions about emergency reporting. As a flood is happening, should it have a place on the website warning people to take shelter, leave, whatever? And we end up deciding it's not our duty to do it. We can only send people somewhere else to get the up-to-date information. So do people want only information, or do they want an advocacy tool? What additional data sets? And how data is collected, more about issues with every single data set, actually, right? You have to explain why 311 is not showing flooding in some areas when there's some. These are all the iterations that the report went through. There was quite many more in between steps, but these are kind of like the main steps in the meetings. I think generally, as the FloodNet data kept on building up, their presence in the report grew and grew. The community members were very interested in understanding it. And some very specific graphs started finding places in it. That one, let's say, is showing just the progression of one single flood event that is chosen by the team. And the very final report that we automated is this one. It's ready to be produced citywide. It's a very simple Python notebook right now. So with a basic Python station, you can run through it and create. Not necessarily inspiration for it, but I think DOH used to publish these community health reports. They were just PDF files listed on a website. That was kind of what our thinking, because the most accessible, simple thing is just a link, you download, PDF comes. Could it be that simple? Can we pre-create all of these reports? They will be prepared. If anything is wrong, we can review it. It's not, we don't have to run any servers on the back end, just very simple reporting. Yeah. And also, one of the very strange things about data visualization is that you have to allow for a very strange data set. You can have a lot of sensors in a region. You can have very few. You can have a lot of flooding, almost none. So a very, very data set, geographically diverse, and creating something that will serve for all of it was quite a bit of a challenge here. And yeah, we learned a lot of things from this. I think, at least personally, as one critique, is that I think you have to go into community meetings a lot better prepared with your questions. If you go and just show things and ask for comments, people will give you comments about things that you might not want to hear. Yeah, I think I would manage it a little differently now, but still was a great learning experience. And you're next?
Yeah.
All right.
Okay, my name's Charlie Midlarts. I'm one of the tech leads on the FloodNet project at NYU. And this is B, who is our fantastic back-end engineer, DevOps, just everything person who's done amazing things. So we're going to talk to you today about our third data product, which is the FloodNet Data API. This is all very beta, very hot off the press, very last 24 hours, some of it. So we're really this is our first unveiling of some of these tools. As we mentioned before, so we do have a ton of data that we've accumulated over the last 3 odd years from a sensor network that's been growing continuously and it's going to grow exponentially this year. We've got a ton of data sitting in a database and we wanted to make it accessible to our various stakeholders. And an API was always a key part of that. And we've finally got around to having an API built out. So we have all the data in Timescale DB. We have Hasura, which is a platform we've used to kind of create the API around Timescale DB. And it's got some kind of early features, but we're trying to work out how people want to access our data. And we've got these 3 key kind of stakeholders in FloodNet. We've got the community who actually suffer from flooding. We've got academics and people in institutions who want to pull data and do analysis. And you've got the city agencies who fund us and want this data for operational reasons. So we're not sure exactly who's going to use the API, but it could be all of those groups. Depends if you're comfortable using APIs. So originally, we had the data in its raw format. It was just lots of zeros. Now and then there was some kind of event. We didn't actually know that there was a flood. We didn't have any means of actually telling that the flood was happening because we hadn't developed these tools. So we were kind of reminded of that when we started implementing alerting tools. So we had this basic system that would say, if the detected flood or the detected depth exceeds some level, send emails to all of our stakeholders, city agencies, people we're trying to impress. And we had amazing realization that this is back in the early days. So there was an event, there was a biblical flood event that happened around the marathon time in New York City, the New York Marathon. And we were detecting roughly 5.5-foot floods that instantaneously happened at exactly the same time throughout the day. And this was because all our sensors are mounted on the signposts right next to the roadways, most of them on the marathon route. So people stood by the road with our sensors above them, we were just getting biblical flooding. So that really was a realization, right, we need to start filtering the data, we need to spend more effort cleaning up our data. Exactly, a different kind of flood, yeah, exactly. We really had to rethink how we filtered the data and processed the data and actually started labeling the data as well. We spent a lot of effort building out tools to flag anomalous events, filters, some basic filters, to machine learning models that we're going to briefly touch upon. And that kind of paves the way. Once you've got that cleaning in place, then you can deliver an API which is useful, which is more event-based rather than just a flood, excuse the pun, of raw data that you need to then sift through. Just to give you an idea of our database structure, we have this hierarchical way of looking at it. We have storm events, so that could be Hurricane Ida, Hurricane Henri, tropical storm event Ophelia, right? There's certain number of events that we've logged in there for New York City. This could be automated, but I think the current version is we've manually just created this database table. Sensor events are events as captured by the sensor. So that's some non-zero flood event. Events could also be noise events, but we have those labeled now. We have flood events, we have different types of noise events, so we can distinguish between something we want to report on and something we want to learn from and ignore mostly. And then we've got deployments, each sensor has a deployment entry in a deployments table. We have information and metadata on each of those. We also have a confidence label, a confidence value, which is the confidence our machine learning model places on that being a flood event or a noise event. So that allows us to help filter and choose what to report on. We also have an annotated by field, so we will have human labels. We do have human labels for these, but as we collect more data, we'll have more labeling happening. So humans actually confirming, yes, this is a flood, this is noise. It can be quite difficult to do, but it's something that can be done. And then we have the depth data on the right. I mean, this is the only hypertable. This is the only time series data, really, in our database. So this is the actual lots and lots of zeros in there. And we have 3 different depth measurements. So we have depth raw, which is like pre-filter, it's like kind of dirty data. Depth filtered has some form of filtering, some basic kind of, if less than 10 millimeters, then make it 0 filter, a really basic kind of noise floor filter. And then depth proc is a process depth value that has gone through a set of heuristic filters which are looking for really steep gradients, which would be caused by a marathon audience member or trash. There's characteristic curves to this data. So floods, just to really briefly give you the idea on the data, flood has a characteristic curve. It's got some physical constraints to it. Water has to come in, come up, and then drain. Blips would be like a person standing beneath a sensor for some period of time. It's just some jump in level, normally with a very steep gradient. A box is like trash or a box placed beneath the sensor. Jump, sit, drop. Pulse train is just, that could be grass, where the sensor is just detecting a surface and then detecting something beneath it, and it's just hopping up and down between those two things. So that's a challenge we've got. Here's some real life scenarios. I hate this sensor with all my heart. This is out in, where is this one? South Jamaica Houses. So this is an amazing spot. It's a dumping ground. It's really unfortunate. This post was put in specifically for FloodNet because it was a kind of high priority location, but we just detect mattresses and rugs and things. So it's very difficult. It's very hard to ignore the noise because it jumps up and down all the time. This was a brilliant one, a child's desk. This was placed right beneath the sensor, so it's a great box scenario. Very difficult to ignore that one. And this is from Google Street View. Always happy to be in Google Street View. There's a sensor there, and there's the trash there, potentially being noise. I'll let you talk about this, B.
So we have our standard filters and whatever, but we also built like machine learning models. This one here is just like a GRU. We experimented with a few other architectures or whatever, but these are primarily for like causal inference, so like real-time prediction of, is it flooding now? We're not currently using this for filtering per se, but we're using this for alerting. So it's not like filtering the data on the dashboard, but it's filtering the alerts that get sent to TP and stuff. I don't know if we need to go into too much detail, but this is just like the confusion matrix between predicting noise and flood event, and the flood confusion matrix is broken down by the like percentage of the way through the flood you are. I don't know, maybe we just head to the demo?
Yeah, definitely.
Okay, so there's different ways for people to access the data. You can always go to the dashboard and whatever, but if you want to get your hands a bit more dirty, or if you're writing an article or something, if you want ad hoc access to specific flood events and you want to pull it and do analysis, you need a solution for that. So instead of writing your own web scraping thing, we just put together an API for people to pull data into their scripts and stuff. Let's walk through this. I guess, where do you start, right? The first thing that may be useful is just to identify the locations that the sensors are deployed in. So we've referred to these as deployments, which refers to a sensor in a specific place with a latitude, longitude, start and end date associated with that. The API is a GraphQL API, which is similar to a REST API. Just the main difference is that it's a bit more expressive. It's somewhere in between a REST API and more like SQL commands and stuff. So here's like an example of our first GraphQL query that we're going to run. We're defining query. We're pulling from the deployments table, and we are pulling these specific columns. So we're getting the name of the sensor, the location, when it was deployed, when/if it was taken down, and the type of the deployment, which is broken down by pluvial sensors or coastal tidal influence. All right, that's the query that we just looked at. So we're just going to make this post request to the GraphQL API, check if there's errors, turn it into a table, parse the dates, and we should have a table of our sensor locations. And then if we want to go and actually look at where those sensors are, we can plot them on a map. So the dark blue sensors with the rain cloud are the pluvial sensors. The sensors that are red are ones that were taken down, and the light blue sensors with the waves are the coastal tidal sensors. So now we're all zoomed in. But yeah, you can see the distribution. These are all of the sensors that we have deployed out there. You can also query the sensors by specific geographic location. So if you don't want to return all the sensors, but you want a specific radius around some latitude and longitude, you can define it like this. So we're just adding like a latitude, longitude, and radius variables, throw those into the query, and we're querying, we're using this deployments within radius function, and we're also filtering down to only include the pluvial and coastal sensors and returning these fields. So that's essentially how that GraphQL query works, and here it is in code. Same thing, we are turning it into a table, parsing the dates, and we get a nice table out of that. And we can do the exact same thing that we just did and plot it on a map. We just queried around the Gowanus Canal, and these are sensors within a 750 meter radius. So now that we know where the sensors are, let's start looking at events, right? So here we're querying the high-level storm events, and these are not associated with any specific sensor, but we can use them to query the sensor-specific events. Same structure. The other queries, we get the name, the start time, the end time, and some free text description of the event. And here's the table of the events that we have. These are sourced from Wikipedia right now, but we will eventually source them from more up-to-date source. And now we can actually look at the flood data, because I feel like that's what people actually care about. So we're going to make another query, and here we're searching by the name of the storm event. So we're passing in the name, and we're using it as a wildcard, so you can search for Ida, and it'll return Hurricane Ida. We're taking the name, start time, end time details of the storm event, and then within that storm event, we're looking for overlapping sensor events. For each of those, you'll get a list of sensor events within that storm event. And for each of those, you'll get the start time, the end time, the label, whether it's annotated by a human or machine learning. And then within each sensor event, you can also get the deployment information, like the name of the deployment, where it is, etc. And then we can also, so that'll return like a table of the events with start and end times, but we can use this next query to return the actual data of the sensor. So you can filter by specific deployments and the start and end time of those deployments. And you can see how this query is working. We're applying the filter, and then with a time greater than the start time, less than the end time. And then here we're returning the time, the process depth data, and the deployment ID for that event. Let's actually run this for some events. I won't show you the Python functions or whatever, but so here we're passing in that wildcard that's going into the query, searching for the storm event, and that returns the metadata around the storm, and then the list of sensor events associated with that storm. That returns these two tables.
How do you name those delightful deployments?
So we just ran the time series query, and now we can plot that on a graph. And these are the sensors that we had up in IDA. We only had a few, but you can see the places that it was flooding. And these are the locations of the sensors that we just pulled. The red is ones that were taken down. Like Smith Street was retired. There's another sensor over there too. So now we can move on to Henri. Same thing, pulling the storm event and the events, the sensor events. And then these are the flood profiles from Henri.
Henri had a very distinct two bump.
Yeah. So that's Henri. And then we have Ophelia as well. So this one, so the other two were back in 2021. So this one's 2023 after we've deployed quite a few more sensors. So now we're seeing an increase in density, right? And it's a bit of a mess, but that's why there's actual visualization tools and not just Matplotlib. So now you can see we're able to source a lot more events, and we can do same thing, plot these on a map. We have more of those coastal sensors, quite a bit more pluvial sensors around Gowanus, Red Hook, and Williamsburg.
True statement, we do not have access to this.
No, I guess for like licensing reasons,
Yes.
we're not allowed to do that. I think we would get in trouble. I know, right?
The title data will be soon included, and that is
We do have.
permissive license. So the title data from USGS and NOAA will be available through this.
because that has a, I can't remember the exact license, but it's very permissive. You can redistribute. The weather data that we gather, which has precipitation, is from Micronet. So it's a subset of Mesonet network of weather stations, and they have some quite restrictive rules around making use of the data. So we have to kind of keep it within our databases. It's quite frustrating, but I think we can work through it. Because they do work very well with other folks. I think we just need to have the conversation. It's not the end of it. It's something we need to work out.
Yeah, and Polly already showed a plot of the tidal sensors, but you can also pull tidal influence events, and you can see how cyclical it is. I guess the last thing is we can also pull some noise events just as some examples for people to see, because as you're using the API, you're going to be seeing different forms of noise. Important to be able to handle that as well. We still have the plots from the last run. So here's some different examples of noise. This might be grass or something. This is in units of inches, I believe. Yeah, there's also just shifts due to temperature and things like that. So this may be due to that since it's pretty stable. So these are some of the noise events that we have to deal with. That's why we have the events table, because with those you can query specific start and end times that are labeled either by humans or by machine learning or automatic processes. So you can.
Where were you based on your IP sensors?
Yeah. If you want the raw from a sensor, it'll give you everything. Just a quick mention that the API, we kind of imagine the API is more for specific focused analysis on events. Because it's limited, we limit how many entries can be returned just to save the server. That's not to say that you can do just like large data gathering approaches by just paging and pulling chunk of data. But we have another way of accessing the data through just CSV files, big like a Google Drive folder where all the data's there, raw, filtered, processed. Something we're trying to work through, and we really appreciate input on is how best to version that data, because we change our approaches to filtering and calibration, and when we do that, we want to make sure that we keep a complete version of the older approaches. It's something we're working on, and we really would appreciate input on how best to version control that data.
So the things that are key by location rather than by events.
Yeah, you can totally do that. We have the geographic queries at the start, so you can start there. Then you could just go straight to the depth table and just query deployment ID, start time, and time, and get everything.
Because of the timescales involved in those projects, we're talking many years for the infrastructure to go in. You're going to cross multiple versions of our filters, our calibration approaches. So it's key for us to maintain the versioning of those.
What does the sensor measure? It snows.
Yeah, I mean, it measures it, right?
So you can distinguish between a flood and snow.
Yeah, I mean, it's a bit tough. We had a big snow event where it was like a lot of mixed snow and rain, so we were kind of worried about that.
Snow is tricky because, for one, it's a brilliant absorber of ultrasound, very well designed to absorb our signal. So what we tend to see is a lot of non-returns, where the pulse will transmit but won't be received or reflected back. So we just see a lot of missing data during snow events. And in terms of the profile, you can still see the overall profile. You see the accumulation gradually falling and laying. Then you have to just dump because the plows will come along and just pile the snow. And then effectively we're blind to flooding at that point because, I mean, if it's going to flood, it's probably going to melt the snow as well. But yeah, snow is tricky, but we're detecting it. It's hard to tell snow. Have we got a snow pass?
No, we were training it over the summer, so we kind of figured we had enough time.
In a few years, that's not going to be a problem.
Yeah, exactly. Yeah.
Oh, so when you have 100 sensors out there, how do you actually detecting the sensor need a repair or calibration? Is there some raw data which is you're not presenting in the API, but you can collecting from the sensor, or is it responsibility from the manufacturer of the sensor to respond to it?
No, it's us. I mean, we are the manufacturing sensor, so we have to monitor all of that. There's a whole set of data that comes from the sensor. Every time we measure we send any measurement, we take the battery level and other conditions of the transmission, like the signal strength and everything. So, and we have dashboards that monitor that. Trends down on battery level, for example, would trigger an alert, and we would have to go out and visit. Trends off of calibration are alerted on as well, so we have to go and visit. Like the process of going from what the sensor actually measures, which is distance, it doesn't measure depth. It measures distance from the sensor to the surface beneath it. We then calculate depth from a change in that in the reference to ground. It makes sense. As water goes up, there's a difference between its normal distance to ground. That can change. The post can move, for example, or they can resurface the ground beneath our sensor, which might add a couple of inches, and we would see that as a couple of inches of flood, but it's not flood, it's just the ground. So there's a whole process that can be done remotely, but mostly, well, partly needs to be done physically, where any anomaly or weirdness needs to be visited or at least scrutinized from the lab first. But yeah, it's a big thing, right? Maintain the health of these things out there. It's a real challenge, but you kind of want the sensors to tell you when there's an issue. You can't be actively looking at the network to discover issues. You have to have a pipeline for alerting the system to make sure that these things in the wild tell you when they're struggling. And we've done some work in the past on involving machine learning on that process. So you feed all of the health parameters into a model, train a model what healthy is versus what healthy isn't. And then when it starts to deviate from healthy, the model should raise flags, hopefully before the sensor goes offline. But at that point, a physical visit is necessary, and that's like time and effort. If you can fix remote by pushing a firmware update or changing the duty cycle to improve its battery performance, that's much better than it just dying, because then you lose data, you have to send someone out. So a lot of this stuff we're not doing yet, but we're going to be doing it when the network grows. Oh, I think we're at time.
Yeah.
This is so cool. Thank you.